Hi, I'm Mark Stephenson from the AVS lab at the University of Colorado Boulder. Today I'll be presenting Quantifying the Optimality of a Distributed RL-based Autonomous Earth Observing Constellation. This work is being presented at the AAS GNC conference in Breckenridge, Colorado. I'd like to take a moment to acknowledge my co-authors, Lorenzo Mantovani, Anish Cheval, and my advisor, Hans-Peter Schaub. So to start off with our problem formulation, we're looking at a multi-satellite agile Earth observing satellite scheduling scenario. So we're given some set of agile satellites on fixed orbits, and the term agile refers to the fact that they're able to slew along track and across track. We have a set of requests, which each of those requests has a fixed location and a priority. And our objective is to assign requests to satellites. This must be feasible with respect to the agility of the satellites, so they need to be able to slew from one target to the other well within the acceptable elevation angle for those targets. And of course, the optimization objective is to maximize the sum of priorities of uniquely imaged requests. So to give a better sense of what's going on, here's a short animation of a few of the scenarios that we looked at. And at the end of the video, we'll return to these results and discuss them in more detail. So to give some background to this work, at a previous GNC conference, we discussed the question of how close can reinforcement learning get to a mixed integer program or an optimal pre-planning based approach on the single satellite agile Earth observing satellite scheduling problem. And we found that yes, RL can do quite well compared to the optimal performance. More recently, we presented on the question of how can we take these single agent policies, which are inherently able to react in a closed loop manner to the environment, how can we leverage that to use them in a constellation? We tried a few methods and found one method that we termed intent sharing that worked the best. This leaves the obvious question of how optimally does this intent sharing method perform? So let's look at these two general classes of methods for satellite scheduling that we considered in this work. First off, we have mixed integer programming. And this is really representative of a larger class of pre-planning based approaches where we plan a sequence of requests that we're going to schedule and then execute it open loop. So the steps here are generally to construct a graph of feasible slews between the opportunities, convert to a mixed integer linear program, solve it quickly and optimally, wait for an uplink opportunity and transmit the schedule to our satellite, and finally execute the schedule, with, of course, the various asterisks of quickly and optimally only really happens on small instances of the problem. The uplink can only happen when we have uplink opportunities, which may mean our plan is out of date by the time we have to upload it. Then we execute the schedule, again, assuming that this open loop schedule works as intended and we don't have new higher priority requests showing up or anything like that. However, these mixed integer linear program approaches are especially useful for this work because they're really great for comparison. The mixed integer program solver returns both the best solution that I've found in some solution times. This is our lower bound on the optimal reward we could collect, as well as an upper bound on the solution, which may not actually be obtainable, but it's the best possible answer that could potentially be found for the problem. So moving to the other class of methods that we use, we're going to talk briefly about reinforcement learning and give really a short introduction or refresher about how reinforcement learning works. So in short, it's learning what to do, how to map situations to actions as to maximize a numerical reward signal. This picture, usually an animation, demonstrates that the first iteration of an agent really can't complete the task at all. But as the agent has more opportunities to interact with the environment, it can learn better and better until it's able to complete a task, in this case, making this bipedal bird-like robot walk. This is really formalized as a Markov decision process. So we have some environment, or for controls people, it's essentially our plant, that returns us some state and some reward for being in that state. The agent then receives that state and has to select an action with respect to that state, which gets passed to the environment. The environment changes based on what action was taken, and a new reward and new state are returned. The goal, of course, is to find a policy, so this what the agent does in response to states, that maximizes the expected value of the sum of future rewards for all states. So for this problem, we need to formalize the agile single agent satellite scheduling problem as a Markov decision process. We start with our observation space, which includes both information about the satellite, such as its current pointing direction, its current pointing movement rate, where it is over the Earth, as well as information about upcoming targets along track. So this might include the value of the request, the location of the request, what times that request is going to be within the elevation angle constraint, and so on. We then, for each of these upcoming end requests, in this work we use 32 based on previous research, we have n actions, one for attempting to image each of those requests. Of course, this action does not guarantee we can complete it because the slew agility constraint may mean that by the time we've slewed to point at the target, it's outside of the acceptable elevation angle constraint. Our reward function is very straightforward. The reward is simply equal to the value of successfully fulfilling the request of that priority. Our transition function is determined from a high fidelity simulation, which we'll talk about a little more later. But in general, this simulation is going to step forward for the minimum amount of time needed, so that we don't waste time. So this means that we're going to either propagate the simulation until we've successfully imaged a target, or until that target is out of the acceptable range, and we better choose a new target to avoid wasting more time on that target. So when we've trained a when we've trained a policy on using this MDP, usually using a traditional off-the-shelf algorithm like proximal policy optimization, we get returned a policy which has some great benefits. It has a low cost of execution, roughly 10 milliseconds per step on a standard CPU. We end up getting closed loop responsiveness. So you need to remember that these policies are not planning out a sequence of actions. They're planning what the next action should be in response to the current state. And finally, we have the benefit that it's learned directly on our simulation of the environment. So unlike the MDP, where we have to go through that process of building a graph of feasible slews and whatnot, this directly learns from any effects we're able to simulate in our simulator. So how do we go from the single agent policy to multi-agent performance? And to do this, we use the technique we call intent sharing. So the idea is that each agent can act asynchronously in the environment, but if we just let them act by themselves, there'd be a lot of conflicts about picking the same high-value targets, therefore wasting time re-imaging targets that we've already successfully fulfilled. As a result, we have to take care to encourage collaboration, prevent competition between these satellites. So we introduced this intent sharing algorithm, which is very straightforward. In general, a satellite's going to pick an action and continue it until it succeeds at the action or fails at the action, as I talked about a few slides ago. However, when we pick an action, when we make a decision, we only make the decision over the set of unclaimed requests. So these are requests that another satellite is not currently attempting to fulfill or has not already been fulfilled by a satellite. So by doing this, no satellite's ever going to be trying to complete a request that another satellite's already also trying to complete. And finally, we just need to modify our local view of the environment by sharing which requests we're currently intending to fulfill so that other satellites aren't going to also try and go to those requests. So moving on to our experiments and results, let's talk a bit about our simulation environment. For this, we use a tool called Basilisk RL, BSKRL, that we've been developing in-house, and it's an environment for satellite reinforcement learning. So we start with Basilisk, which is an AVS Lab simulation tool that's a fast and flexible simulation framework with a great Python front end, a C++ back end. So we get the flexibility of Python, but the performance of C++. We combine this with Gymnasium, which is a standard reinforcement learning environment interface. And as a result, we get BSKRL, which is a configurable way of creating environments for satellite tasking reinforcement learning research. Really inherits the best of Basilisk and Gymnasium. So we get our modularity of our spacecraft and our environments from Basilisk. We get the high fidelity simulations where we can very easily go from, abstracting away things like sensor models or reaction wheels to fully modeling that level of fidelity to the dynamics. And then, of course, we get our compatibility with our major reinforcement learning libraries from Gymnasium. So in this case, we particularly like to use RLlib due to its great scalability. If you're interested, we have a link here and a QR code that'll take you to the documentation for the latest version of BSK RL. To go into the specific experiments we're running, we're considering the Agile Earth observing satellite scheduling problem over a variety of request types. So we have our uniform requests, which we will consider uniformly distributed requests over the surface of the Earth, ranging from 100 to 10,000 requests globally. And then is a way of standing in for a more realistic distribution of, scientific or defense points of interest. We look at a map of cities. So these requests are representative of any sort of data set where your requests are going to be highly clustered in certain areas and fairly sparse in other areas. For our constellation configuration, we primarily considered a string of 4 satellites with a varying true anomaly spacing. In particular, we look at a 0.1 degree spacing, a 10 degree spacing, a 1 degree spacing, and a 10 degree spacing. And for comparison, we give our mixed integer linear program solver 2 hours to compute a solution and an upper bound for optimality. And for the reinforcement learning policy, we just let it run a closed loop on each satellite using that intent sharing method, taking again about 10 milliseconds for every decision that a satellite makes. Very realistic to be able to run it on board in the loop. So let's look at the relative performance of the two methods. We're going to start out by looking at this x-axis or the y-axis, which gives us a ratio of how well the reinforcement learning algorithm performed to the various mixed integer linear program results. The solid lines are going to be the comparison relative to the solution the mixed integer program found in 2 hours, whereas the dotted line is going to be how well it did compared to the upper bound that the program found in 2 hours. As a result, the true optimality is going to be somewhere between the dotted line and the solid line, but in realistic operations, you're probably not going to be able to let your solver run until it finds an optimal solution. So it is somewhat reasonable to compare it to that upper line of the 2-hour solution. We see that on the uniform requests on the left plot, we between 0 and 5,000 requests uniformly spaced, we get excellent performance. Across the different variations of the constellation, we find that the constellation performs roughly the same as well for the mixed integer result, the upper bound of the result showing that it nearly converged, and the intent sharing method. So that means that we're able to get this closed loop, very fast solutions in this distributed autonomous architecture that are nearly optimal. As we go to higher target counts, we see some interesting behavior, in which cases the reinforcement learning-based method actually performs better than the solution that was able to find in 2 hours, because the mixed integer program starts to take very long to converge as the problems get larger. Compared to the upper bound, we're not doing perfectly, but we're still doing quite good. We see that we're doing at least 90% of optimality and very likely higher than that. Moving on to the city requests on the right side of the plot, the performance is somewhat depressed compared to the uniform request, but still very good. We're still seeing within 90% of the solution that the mixed integer solver found, and within 80% of the upper bound of that solution. This type of problem tends to be harder for the reinforcement, this distribution tends to be harder for the reinforcement learning-based approach and easier for the mixed integer linear program approach, because the dense clusters of targets can be more easily decomposed by the mixed integer approach, while they present a challenge for the reinforcement learning-based approach that only gets a short horizon to consider of upcoming targets. Finally, let's look at the red line. In both cases, we see that this red line, which represents the single satellite performance of the reinforcement learning algorithm compared to a single satellite mixed integer linear program, we see that the multi-agent system with intent sharing actually does better than the single agent method does. What this really implies is that we're able to leverage the good behavior that we learned in that single satellite case, but by introducing more satellites, we're able to essentially unburden the single satellite and get the remainder of the performance without having to solve a very challenging multi-agent scheduling problem. Let's move on to the videos of the results that I showed initially that reflect some of these cases. So first, we're going to look at these 900 city-based requests with 10-degree satellite spacing. We see that in this case, the targets are generally sparse enough that the first satellite tends to pick up all of the many of the targets, which were getting marked in red, and the second one in green was getting most of the remainder. When they're closer together, they're in conflict for the same targets more often. So we see a better distribution of targets across the different agents in the constellation. The uniform requests likewise show that when the satellites are spaced close together, they end up cooperating very well to pick up nearly all of the requests that are available to them. We see this again when we're looking at the 10,000 uniform requests. So really there's one conclusion to this paper, which reflects that initial question we asked, which was, can we do as well using this federated autonomous reinforcement learning-based solution compared to an optimal solver? And the answer is yes, we can use this intent sharing method to achieve closed loop performance that is very competitive with these open loop global solvers. And of course, we get all the benefits of using a closed loop solution where we can update our request list at will. We can respond to unexpected high value events. We aren't locked into some open loop solution that was pre-computed hours ago. Thank you for listening. If you're interested, please find the paper on the AVS Lab website or contact me with any questions.